Hey guys, today we are talking about the ambiguous case. And basically what this is it's a special subset of the law of sines. And we're going to kind of review a little bit of geometry to talk about why this is true. But you're going to ask yourself what type of oblique triangles, that means non-right triangles, have no solutions or have multiple solutions. So, going back in time and talking about when you proved triangle congruences. So remember, when you proved a triangle congruence, you talked about what pieces of information you had for each triangle, whether it were angles or sides. And there were a couple of them that you could use to prove those triangle congruences. And so for the law of sines, we're actually using some of those pieces of information, where, for instance, on last night's assignment, they gave me, in a triangle, call it ABC, they gave me a side and they gave me the two angles around that side. So you had angle, side, angle. Angle, side, angle. And that was an okay way to prove a triangle congruence back in the day too. If you could prove these three pieces were the same, then you knew your two triangles were the same. Okay. The other one that we've been using with the law of sines would be when I had an angle and an angle and then a side. Well, I put S. Oh no, where'd all my stuff go? I meant to put little b. Okay, and so we've been using those the last day because we could set up my proportions still, where then I'm just looking for one missing side versus looking for all the missing sides. So this one would be angle, angle, side. So this is enough information to use my formulas, and it's also enough information to use to prove a triangle congruence. Okay, same deal with the law of cosines. Again, we've been doing this with on the other day. And so when I had a triangle and I knew the side and the angle contained between the two sides, and so that is side, angle, side. So when you had a side, the angle between, and then a side, that could prove a triangle congruence. And that also, when we used that law of cosines, which you have on your formula chart that said c squared equals a squared plus b squared minus 2ab cosine c, that worked because then I'm just looking for this c. And also we could use the law of cosines if I knew all the sides, so a, b, c, because then when I'm just looking for that angle, I can just do the inverse cosine. So all of these were legitimate ways to prove that to prove that a triangle is congruent, and they're also legitimate ways to use our law of sines or use our law of cosines. Okay, but there were two different triangles that didn't work out for us. The first one was the one where you had all your angles inside. So angle, angle, angle. And if you remember back to geometry, you could make an infinite number of triangles that had those three angles. And so we could prove that the triangles were similar, but not that they were congruent. So angle, angle, angle is not going to work. The other one that we had an issue with is when I had an angle and then a side and a side. And so we wrote that one as SSA. You can see what would happen if I had written it the other way, but this one would always give me two different answers when we're trying to prove triangle congruences. And in this case, we also might get two different answers using the law of sines. So this is your ambiguous case. So the angle that's given is not between the two given sides. This is called the ambiguous case. So when this happens, you have to double check, because you can either have one triangle that works for this, two triangles that work, or no triangles that work with those given pieces of information. Okay, so let's do a couple of examples. There's three different types that we're going to see for this. Okay, the first one here, it says that, well, I want to do this. For the first one, gives you some measures and some sides, and we need to find y. So I'm going to go ahead and draw my triangle, shockingly enough. This is x and then y, z, and I'm going to label what I know. I know that x is 27 degrees, the side opposite y is 5, and the side opposite x is 4. So if you notice, we're getting that angle side side thing going on where we don't like that. So what we're going to try to do here to find angle y is we're going to use the law of sines, which you have on your formula chart, and basically we're just going to set up that proportion. So since I want to know what is this angle, I'm going to set up a proportion with y. So the side opposite y is 5. And then I'm going to use the other thing that I know. So then I'm going to take the sine of x, or the sine of 27, all over 4. Then you just have to cross multiply and solve this. And yes, you can still use your calculator for these. So I would get that this is 5 times the sine of 27 is equal to 4 times the sine of y. Divide both sides by 4, and then we'll take the inverse sine of that. So when I go to my calculator, if I'm going to do this piece, I'm going to take 5 times the sine of 27. Make sure you close your parentheses. I'm going to divide it by 4. You're going to have to be really careful here, because on your paper, you're probably going to write down that I want to take the inverse sine of 0.567. But in your calculator, please, please, please try to use the answer button. So you're going to take second sine and then do second negative, and that's going to just pull that answer from before. So I find out that that angle is, if we round to the nearest whole one, we'll have 35 degrees. Okay, so the big problem here is, just like when you take a square root on your calculator, you know that when you take a square root, you get a plus or minus answer, but your calculator doesn't. It's always going to give you the principal square root. This is giving you the principal inverse value. And so if I think about on my unit circle, it's given me the angle over here. But you also, because sine is positive in quadrant 2, you have a reference angle of 35 degrees over here that would give me that same ratio. So 180 minus 35 would be 145 degrees. And if I checked that in my triangle, 145 plus 27 is still less than 180, so that could get me a whole nother triangle. So what your calculator has done is it's given you the principal inverse value. You have to remember that there are 2 places where sine is positive on your coordinates here, and so now measure of angle y, we could have 35 degrees or we could have 145 degrees. So there are 2 answers for this one, because they both made legitimate triangles when I used both the principal inverse value and the one in quadrant 2. Okay, now that we have that piece, if we want to try to solve for a missing side length like z, then what I'm going to have to do is take both of those cases into account. So I'm going to have one triangle that has all of the things we knew. So this is x, y, z. We have 4, 5, 27 that was given to me. And I'll have to do my first one that has y is 35 degrees. Okay, and so then this is just a law. We can use the law of sines, we can use the law of cosines. I'm going to go ahead and use the law of sines here. Because I know that the angles of a triangle add up to 180, I can just do 180 minus 35 minus 27 and find out what angle z is in this particular triangle. So that's 118 degrees. Then I can find the side across from it. So I'd have sine of 118 over that length z, and then I would use the one that's given to me, just because what if I did make a little mistake. So I would use sine of 27 over 4. If you cross multiply and solve this, you would find out that the first value for z is 7.78 if you rounded to the nearest hundredth. Okay, so we're just cross multiplying and solving. Okay, but that's not the only case right here. We found out that there were 2 possible answers, so that means there are 2 possible triangles. So I would draw my triangle out one more time. So this is this is x, y, z. X is 27 still. These guys are still 5 and 4. But now, because of the other answer I found, y could also be 145 degrees. So if I do 180 minus 145 minus 27, I will get that this guy would have been 8 degrees. Okay, then I set up a very similar proportion, but now it's going to be the sine of 8 over z equals sine of 27 over 4. Once I cross multiply and solve on this, I would find out that my other value for z could have been 1.23. Okay, so your first case is when you get 2 triangles or 2 angles, and then they both work out and they both make a triangle, so you have 2 separate triangles that you have to solve out. Okay, the second one is going to be measure of angle x is 27, then 5, 6, and then we're solving for z. So first thing we need to do is draw my triangle. x, y, z. So we have 5, 6, and then x is 27 degrees. Again, we have the angle side thing going on. And so once I go ahead and figure out my law of sines here, I'm going to take the sine of 27 over 6 because that's what's given to me. And then what I'm looking for is side z. So I need to have that angle first. So I'm going to go ahead and use the thing that I was given to find this angle before I can find z. So I would take the sine of y and find over 5, so that way I could figure out what that last angle is and set up a new proportion. Okay, so then I do all my business here, and I would have taken the inverse sine of 5 sine 27, not y, struggling, over 6. And then when I plug that in my calculator, I would get that that is approximately 22 degrees. Okay, so that's my first option for y. Y could be 22 degrees. Now, if I went in here and I thought about my second angle that would work out, 180 minus 22 would get me to 158. Now, if I look at what already exists in my triangle, if I take 158 plus 27, that's going to get me a number that's bigger than 180. And so since 158 plus 27 is greater than 180, this isn't going to make a triangle. So for this one, I only have one possible answer because I can't build that triangle that has those specific angles in it. So for this one, you only get one solution because your second angle didn't actually do anything useful. Okay, so we've seen two solutions and now this is one solution. We can go ahead and set up that proportion to solve to find out what side z is. So we would have the sine of 27 over 6, again I'm going to use the things I know, equals to, I could find that last side by taking 180 minus 27 minus 22 and finding that's 131. So then I'd have the sine of 131 over side z, and I would find out that side z is approximately 9.97. Okay, so this is on the ambiguous case. You can have one solution, you could have two solutions, or perhaps you can have the number of solutions in this last example. So again, we're going to draw my triangle. I'll get a different color. So I have x, y, z, 27, 5, 2, and I want to solve for z. So if I go ahead and I set up my proportion again, remember before I can get to z, I'm going to need that angle y. So I'm going to take the sine of y over 5 equals to the sine of 27 over 2. I'm just taking the pieces of information I know and plugging them in. Okay, so then at this point, if I did my cross multiplication here and I got 5 times the sine of 27, and then I'm going to divide that by 2, I would know that the sine of y is equal to 1.13 blah 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 blah. Okay, but if you remember back to our inverses in there, and I think about a sine value, you cannot have a sine value that's bigger than 1 or less than -1 because that sine graph I had never went above 1. My unit circle never goes above 1. And if I try to take the inverse sine of this in my calculator, it's going to yell at me and say, you can't do this. And so since you can't take a sine that's greater than 1, this triangle has no solution. There is no way to make this triangle work with any of the constraints that they've given me. So the hardest thing about the ambiguous case is remembering when you are setting up to look for that second answer, to look for not just the principal inverse value, but also to find that second answer, to take 180 minus it, check if it makes a real triangle, and then you decide, how many triangles do I actually have to solve? 1, 2, or maybe even none. Okay, I will see you tomorrow in class.